Right, we're going to look at some examples of applying gravitational field strength. So let's look at this. So we have Betelgeuse. It is the 9th brightest star in the universe. It's a red supergiant. It has a mass of 7.7 solar masses, one solar mass being 1.99 times 10 to the 30 kilograms. And it has a radius of 1,180 solar radii. And we're told one solar radius is 6.96 times 10 to the 8 meters. So we are going to determine the magnitude of the gravitational field strength on the surface of Betelgeuse. So to do that, we need the total mass and we need the total radius. Well, we're told that the mass, it's 7.7 solar masses. This symbol here, the dot with the circle, this is just kind of astrophysical notation for sun. So the total mass is going to be 7.7 times 10 times 1.99 times 10 to the 30 kilos. So we have 7.7 times 1.99 times 10 to the 30, and that is going to give me about 1.5323 times 10 to the 31 kilo. And then the radius, we're told it's 1,180 solar radii. So we're going to have 1,180 times 1 solar radius of 6.96 times 10 to the 8 meters. So then this is going to give me about 8.2128 times 10 to the 11 meters. So now I have my values for the mass. I have my values for the radius between the center of Betelgeuse to its surface. So now we can determine the gravitational field strength, its magnitude. So we just have this gm over r squared. So we're going to have this 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We have that mass of 1.5323 times 10 to the 31 kilos. And then we're going to divide that by this 8.2128 times 10 to the 11 meters. And then big thing, don't forget, r squared, so do not forget that squared there. That will definitely change your answer. So we are going to divide this by that. And what we get is we're going to get a really small number. We're going to get about 0.00152 newtons per kilogram. Or if you want to write 1.52 times 10 to the minus 3 newtons per kilogram, that's fine too. Or if you want to put meters per second squared instead of newtons per kilogram, that's also fine. So a follow-up question might be, Betelgeuse is pretty massive. Why is its gravitational field strength pathetically small? Keep in mind, A, this is an oversimplification. Because of its massive size, we also should be dealing with general relativity. That's one big thing. But the other thing is Betelgeuse, even though it's really heavy, it's also really large, so it's not actually that dense. But the not using general relativity is certainly limiting us, and at the high school level, we certainly aren't going to touch that one. That's for university. So last one here. So we get the gravitational field strength at the surface of Jupiter. It's approximately 25.9 Newton per kilogram. So Jupiter's got a mass of 1.90 times 10 to the 27 kilos. We want to determine its mean radius. So the gravitational field strength, it is going to be G times m divided by r squared. Our objective here is to find r. Now, because r is in the denominator, we are going to want to bring this up top first, the r squared, and then isolate for it. So we're going to multiply both sides by r squared. So that's going to take care of that here. What I get is G times r squared is equal to big G times m. Now that I have the r, or the r squared rather, up top, now I can begin to isolate for it. I can divide both sides by this magnitude of the gravitational field strength. We get rid of that, and that gives us r squared is equal to gm divided by g, or gm divided by little g. And then last thing, we don't want r squared, we just like r. So the radius is just going to be the universal gravitational constant times the mass of Jupiter divided by the gravitational field strength on the surface of Jupiter. So we've rearranged. Last thing, we just want to start to plug some things in. So we got this 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared that mass of Jupiter, that 1.90 times 10 to the 27 kilos, and then the magnitude of this gravitational field strength, 25.9 newtons per kilogram. And of course, we want to square root that whole thing. And again, just like when we were doing stuff with universal gravitation, Newton's law of universal gravitation, if your answer seems a little funny, your gut's kind of telling you something's gone wrong, like I said, trust your gut. The biggest mistake that happens with these type of questions is not square rooting. So don't forget your square roots. Squares and square roots seem to be the killer of students in Physics 20 and 30. But alas, we are going to get a value of about 1, 2, 3, 4, 5, 6. So we're going to get about 7.00 times 10 to the 7 meters. So that's what we're going to get for Jupiter's mean radius. Seems pretty reasonable. We can be fairly confident in our answer. Now you might say, these questions are pretty easy, they're not very hard. The next example will show you where we're trying to trick you. Stay tuned for that.